Hello, everyone, and welcome to another Jakarta Tech Talk. My name is Serena, and joining us today is Rich Haggerty, who will be presenting on the topic of To Instant On and Beyond, Java at Lightspeed. If you have any questions for Rich as we move through today's presentation, feel free to ask them in the chat or in the Ask a Questions tab. Rich, without any further delay, over to you.
So hello, everyone. Again, my name is Rich Haggerty. I'm a developer advocate at IBM. It's my pleasure to be here today. So the title of my talk, again, is To Instant On and Beyond, Java at Lightspeed. So obviously the theme for my talk is around making Java apps faster. And by fast, I'm talking specifically about startup time. So first off, why do we really care? Well, for traditional Java monoliths, we really don't. It's not that big an issue. I've seen Java apps that take 10 minutes to start up, but it really isn't a problem because in production, we don't do it that often, right? That's one of the main benefits of Java. The longer we let it run, the better it runs. But what happens when we want to take advantage of cloud-native distributed architectures like microservices and serverless? So now startup time is crucial. So our Java apps need to instantly scale up and down based on usage and demand. But speed doesn't happen in a vacuum. It does require some underlying technology so that we can build optimized containers with low memory footprint and high CPU throughput. So what are these technologies that can make that happen? That's what we're going to be talking about today. So first, we're going to be talking about application or architecture styles, and then the runtimes that support them, such as Open Liberty. Then we'll cover the issues that are inherent in Java that make it great for monoliths, but not so great for distributed architectures. Finally, we're going to cover the technologies that solve some of these issues. And hopefully, God willing, we'll have a couple of live demos. Let's start off with application styles, architecture styles. So there are many ways to architect a business application and many application runtimes available to support them. So we have our traditional monoliths, which are single self-contained applications. A lot of folks treat monoliths as old school or legacy, but believe it or not, it's still the most popular architecture for Java developers. Microservices is breaking that monolith up into 2 or 3 large applications that interact. But typically all these parts stay together and are developed and deployed like a monolith. So then we get into microservices, which is definitely gaining in a lot of popularity, mainly because it allows you to take advantage of the latest cloud platform technologies. Microservice architecture is a number of loosely coupled services that can be scaled up or down based on demand. And another big advantage is that each service can be independently developed, maintained, released on its own schedule without affecting the other services. So each of these styles have their pros and cons, but they all must run in a Java runtime, which leads to our next slide. So all applications are executed in some sort of application runtime, and there are many Java runtimes to pick from. Typically, all Java runtimes are optimized for a particular type of architecture style. So for example, traditional WebSphere, JBoss, WebLogic, I'm sure we've all heard of them. They've been around for decades. And they're built for traditional monolith applications running on dedicated servers loaded with resources, right? But as we move further to the right, we need additional capabilities, features that Java has historically struggled with. To play in these spaces, you need to have fast startup times, low memory footprint, and high throughput at ramp up. So this is interesting. So one of the most exciting things happening in the Java space right now is what's happening here on the right side of the chart, or to cover these types of architectures shown on the right side of the chart. So there are tons of solutions that are coming out recently to specifically address this issue. I'm sure you all have heard of GraalVM, Native Image, Crack, Orcus, Microdot, Helidon. So they all claim to answer, they all claim to be the answer for deploying your Java workloads to fit these new cloud architectures. But they all have different approaches with different frameworks, which means different syntax, rules, configurations, and maybe they're only focused on one specific use case like microservices or functions. So maybe you need to learn more than one. Who knows, right? So is there a better solution? Maybe there is a single Java technology stack that works for all of these architecture styles. That's what we're going to get into next. So if there was one runtime that could satisfy all these architecture styles, it would at a minimum have to have the following characteristics, right? It'd have to have a modular runtime, which means less resources. We need small footprints, but high throughput to minimize costs. It must be optimized to work with all the major players in this space, from the cloud platform providers to the cloud native tools like OpenShift, Docker, and Kubernetes. And it must provide a simple and powerful developer experience. So things like plugins to all the popular IDEs and support for non-proprietary or vendor-neutral APIs like Jakarta EE and MicroProfile. All these things make the developer's life easier. So how do the modern runtime stack up? So today we're going to dig deeper into one of these, which is OpenLiberty. So again, OpenLiberty is a lightweight open framework built for cloud native apps. So OpenLiberty is an IBM open source project and the upstream project for IBM WebSphere Liberty. So there's a lot of confusion around this. There's a WebSphere Liberty and an OpenLiberty. Both use the same base, use the same code base, but WebSphere Liberty has a little different, has some additional features to satisfy customers coming from traditional WebSphere. So when I refer to Liberty, I'm talking about OpenLiberty or WebSphere Liberty. Also, the OpenLiberty was open source in 2017. And it is free to download and use. So we try to emphasize the main reasons why you'd want to go to Liberty. And we're going to go through each of these. But basically, it's lightweight, highly efficient runtime. We have it's optimized for CI/CD, and it has a really good developer experience. So let's take a look at the Liberty architecture and how that was designed. So Liberty is a modular Java runtime consisting of a small, lightweight kernel with many optional features to provide runtime capabilities. So essentially, in the old traditional application server, you would be writing a Java EE application, for example, and that would bring you the full stack. You would have to load that into your runtime. But with Liberty, it's more modular. So again, we start with a kernel, and then you just define the features that you need. And when you say, for example, here we need CDI 4.0, it's going to bring in that particular feature and things that it depends on. In this case, it's App Manager. And as you add more and more features, you're going to pull in more and more libraries. So the end result is you're going to get exactly what you need. You won't have to pull in anything that to add bloat that isn't needed, that isn't required. So this is ideal for running in containers when size matters. So let's talk a little bit about CI/CD. There's two main concepts I want to talk about. We have zero migration, which means basically that you never have to migrate. You can grab the latest release and nothing should change your code. No configuration changes, no behavior changes. So if you just want to get the latest release with security updates, for example, you do not have to change your code and it should continue to work, or it will continue to work. Liberty has a continuous delivery cycle, so it's released every 4 weeks. New features and security fixes, obviously. So the big part about this is it eliminates technical debt. There's a lot of developers cringe at updating to the latest release, but we've taken that away with our zero migration policy. So as far as developer experience, we are integrated with all the right tools, all the IDEs, your Maven Central, Docker Hub, all the build tools. Again, the API, including Spring Boot, and all the testing frameworks. We also have this feature called Dev Mode, which allows you to, from your IDE, run the application server in the background, and it automatically detects any code changes, including configuration changes. So once you're in this mode, you can make code changes and not have to worry about, did I stop and restart my server to see my changes? So basically you have no rebuilds, no redeployment, no install, no restart. So you just code. So again, Liberty has you covered for all phases of the DevOps lifecycle, whether you're doing DevOps or not. Again, these are all the tools, and notice here all the clouds that we tie into automatically. Now let's talk about Java on cloud and some of the issues we have there. So is Java on cloud always a good fit? So again, traditionally, Java wasn't focused on startup, which is happening up here. It's mostly a concern with steady state, meaning we want to get your Java application up and running, and then we want to optimize it for the long run. So if you look at architecture styles versus typical Java workloads, so here are the architecture styles here, and the characteristics of the style, and whether we think traditional Java runtimes are compatible. So for monoliths and microservices, which are all long-lived, want to be efficient, yes, it fits very nicely. But we get to microservices, we now count on, or we need, fast startup, ramp-up time for scaling up and down, including to zero. To meet demand, we need a very small footprint. We're not sure about the typical runtime probably can't handle that. And if we're being honest, we're going to say it doesn't. And for serverless functions, obviously we need fast startup time in milliseconds. So it obviously can't handle that. So in order to understand why, let's dig a little deeper into the JVM. So we're all Java developers, so we know what this is, but we'll go ahead and level set on some of these. I want to level set on how the JVM actually works, so we can talk about some of the solutions, so we're all on the same page. So basically, the JVM is the heart and blood of Java. So it's responsible for taking your application bytecode and converting it to machine code for execution. And the beauty of the JVM is it allows you to write your code once and run anywhere, wherever there's a JVM, right? So your Java code you could take to different machines without having to change the code. So how the JVM works, you take your Java code, you compile it with Java C, and you get your bytecode, which is then passed to the JVM for execution. And again, there's a JVM for every type of architecture and operating system. So as your code is, what the JVM does is it loads all the classes needed to run. It verifies the bytecode that's been passed in, and then it executes the code. Initially, this is done with an interpreter, which means it's executing byte by byte, which is relatively inefficient and slow. So how does it get around that? How does Java make up for this? Well, it has this just-in-time compiler, this JIT. So as the code runs, profilers are sent out into the environment, determine code paths, and we identify hot methods that should be compiled. So if a method is called over and over, it's going to be sent to the JIT for compilation, so it gets compiled down to machine code. And a machine code is 10 times faster than the interpreter is. And the thought is, as the longer your code goes, the profilers learn more and more about your environment and the code paths it's taking, and can compile just the right methods so that your application runs smoother and more optimized. So let's talk about the good and the bad of the way that works. Hold on. I got a security update there. Sorry about that. So the JVM. So let's talk about the good things. It is device independent, which means we can write our code once and run anywhere. It has been around for over 25 years, so that's a lot of years of improvement. The JIT does produce optimized code through the use of profilers. Again, that optimized code is better than anything you get through static compilation. It has very efficient garbage collection, and the longer it runs, the better it runs. So the JVM collects more profile data, and the JIT compiles more methods. So the downside to this approach, especially with related to containers, that initial execution run is interpreted, which is relatively slow. The hot methods that are identified to be compiled by the JIT can create CPU and memory spikes. Those CPU spikes cause lower quality of service. Memory spikes cause out-of-memory issues, and the leading cause of Java crashes is out-of-memory issues. This all results in slow startup time and slow ramp-up time. Just to be clear, startup time is the time that it takes your application to load, application code to load. Ramp-up time is the time it takes your application to actually compile all the methods that it needs to run. So ramp-up time is the time it takes to get to an optimized state. So here's some charts of what I'm talking about with these spikes that occur in the JVM. So the left side is the CPU spikes, and the right side are the memory spikes. And as you can see, they all start at the beginning, and they're all associated with JIT compiles. And as you notice, the more that we get the compiles completed, we get to a steady state. So understanding that we have these spikes we have to deal with, how do we provision containers? How do we determine what size to make our containers? Well, obviously, we're going to have to over-provision to avoid these out-of-memory issues. But how much? We're not sure, right? Very hard to do. JVMs have very non-deterministic behavior, meaning you can run the same application multiple times. You're going to get different spikes, different places at different levels. So it becomes kind of a guessing game, how big to size your containers, but you will definitely need to over-provision. And once your code gets to steady state, all that extra memory is going to be wasted. So there's also an issue with horizontal auto-scaling, like with Kubernetes. And when I'm talking about auto-scaling, I'm talking about scaling up and down based on demand. So there's two issues that hamper scaling. First of all, the slow startup and ramp-up times make it inefficient. Also, those CPU spikes we talked about, they can cause some false positives. Basically, the CPU spike, so typically, you would set your thresholds for scaling at a CPU level. So say, for example, 50% CPU, we're going to spin up another instance of my service. But what happens when we start up that container and it goes over 50% just to handle JIT compiles? So now we're incorrectly launching additional instances, not based on demand, but because our particular container is doing JIT compiles. So there's two solutions to that, right? So both inefficient, both suboptimal. One would be to set your CPU level higher to say 75%. That's going to be a waste, right? So we're not going to be able to handle spikes in demand very efficiently. The other is to just have extra instances lying around, always started, just to handle those peak periods. Both of those are inefficient. So how do we solve this problem? So obviously, it's if it's not obvious to you yet, here's what we got to do. We have to minimize or eliminate the CPU and memory spikes, and we need to definitely improve those startup and ramp-up times. So before we get to the solutions, let's talk about the underlying technology that supports Open Liberty, which is the OpenJ9 JVM and Samurai runtimes. So again, OpenJ9 JVM from Eclipse Foundation and IBM Samurai runtimes, which is our OpenJDK distribution, are the foundation for Open Liberty. So let's talk a little bit about the Eclipse OpenJ9 JVM. Again, it was open sourced about, I think, 5-6 years ago. It began life as the IBM J9 JVM. It was designed from the start to span all the operating systems needed by IBM. So IBM learned early on that Java was going to be popular, and they wanted to be able to run on all their devices. This includes mainframes all the way down to handheld scanners. So the JVM obviously had to be designed to go from very small constrained environments to large ones. And it was developed over 20 years ago. So all the Fortune 500 companies that run enterprise Java are running on OpenJ9 JVM. Again, it was open sourced about 5 years ago, and it was renamed the OpenJ9 JVM. So that is distributed with IBM's OpenJDK distribution called Samurai runtimes. The name Samurai comes from Mount Samurai, which is the tallest mountain island of Java. So IBM has a runtime. They call it Samurai runtimes. They used to be called IBM JDK, IBM Java. And it's built just like all the other distributions, and is based on OpenJDK, but obviously it includes the OpenJ9 JVM. So when we talk about distributions, I always ask developers where they get their Java from. A lot of them are confused, which is because up until a couple of years ago, basically everyone got their Java from Oracle, but they changed their model, their support model a couple of years ago, or their licensing model a couple of years ago, to try to get some more support dollars. So other vendors said, you know what, we can also do that. We're still going to pull in the OpenJDK binaries, and we'll distribute it for our customers with our own support packages. So these are some of the distributions that are currently available, some of the more popular ones. Again, this is kind of a new thing that's only come out for the last couple of years. So IBM Samurai runtimes is another one of those. IBM's is geared toward obviously having OpenJ9 JVM, but it also has builds for some of their higher end systems like Z and Power. And you'll find that across the board with these other distributors too, right? So like, for example, Amazon Corretto is tuned maybe to work better on AWS. You got Red Hat has, theirs is tuned to work better on RHEL, and Microsoft's for working on Azure, right? But they're all typically the same. They all include the OpenJDK binaries, and very little difference between them. They all usually run the Oracle Hotspot JVM. IBM's the only one that comes with the OpenJ9 JVM. So now that we understand we got a little intro on the issues with Java. We talked about Open Liberty and its foundation pieces, which is the OpenJ9 JVM and summary runtimes. Let's talk about some solutions. The first is going to be the Samru Cloud Compiler. And this is a good solution for microservices. So essentially the concept here is that the cloud compiler pulls the JIT out of the JVM and makes it as a service. So it's essentially JIT as a service. Shown here in this diagrams on the left, you see we have multiple clients, all with their own JVM and local JIT, which they're turning off, and they're going to have their JIT serviced by this one service here. Now, the JIT is turned off, but if this connection does go down for some reason, it does have access to its local JIT, so you will be able to continue on. So the big advantage here is that we have a smaller footprint, right? We don't need to contend with all these spikes. So the orange is one of these clients here that are using the JIT as a service for the Samru Cloud Compiler. You notice it's a lot more flat, and we can easily provision around this. It's hard to provision the right size container for these spikes, but not for the orange line. So one of the main benefits you get from this is that you have smaller container sizes, which means application density into nodes. And actually, I'm going to show you in my next slide, which shows you a good experiment for this. Oh, I wanted to mention that it's really easy to turn on. Open Liberty comes with a operator, a Kubernetes or OpenShift operator. If you're familiar with those, it makes life a lot simpler. But essentially, if you have that installed, you can turn on the Samru Cloud Compiler with a simple enable true in your YAML file. So here's an experiment we did. Basically, this is hard to read, but the top portion here is without using the Samru Cloud Compiler. We essentially have 5 Java applications running, each with 5 instances. And the containers are sized to run efficiently for that application. We determine what size was required. For example, this is Acme Air monolith application, and it needs 500 meg of memory to run. And we have how many instances? We have 8 instances running across 3 nodes here. So the default configuration required 3 nodes. Now we use the Samru Cloud Compiler in the bottom row here. Now you'll notice we still have the same applications and the same number of instances running, but notice how much smaller they are. We basically require half the memory, so we can make our containers smaller. Therefore, we can move more containers into a node, and we've eliminated the need for an additional node. And if you look at the brown box here, this is the JIT or the Samru Cloud Compiler running. It's usually the largest container. It needs a couple of gig, but it's servicing all of these clients here. And we ran tests on this, and both the performance of all the applications in both scenarios was about the same. So what we did, we basically saved 33% in resources to get the same performance. And one thing we haven't really touched on with moving to the cloud is cost. Resources. We're always trying to minimize cost. So here's another chart that shows the advantage of using the Samru Cloud Compiler for auto-scaling. So as you can see here, we have all the spikes, the plateaus occur once we get to a new instance needs to be fired up. And the blue is with the Samru Cloud Compiler, the red is without. And you can see the blue, the spikes are not as deep. We ramp up a lot quicker, and we get to steady state quicker. All right, let's get to a demo. I'm going to exit my. Okay, let's see if this works.
It does.
Okay, we see everything. All right, so this is what we're. Okay, good. So this is what we're going to be showing here. This is a example of running applications in containers with access to the Xamarin Cloud Compiler. You'll see this term JIT server a lot. Basically, that's the OpenJ9 name for this technology. We call it Xamarin Cloud Compiler when it's combined with OpenLiberty and Xamarin. For this example, we're going to be running 3 versions of this application in containers. The first one we're going to run with 400 megabytes. The second one, we're going to try to run it in 200 megabytes. The third version will also have 200 megabytes, but it will have access to the Xamarin Cloud Compiler or JIT server. It's the only one. So all these other boxes are just support containers or processes to help with this experiment. JMeter is what's going to be feeding the demand to these containers. And Prometheus is going to gather some metrics, which we're going to be showing in Grafana. Okay, so here comes the tricky part. I'm going to be scooting around to different windows. Let's see how this works. I need to first get to my system. Need to start up Grafana. Sorry about the zooming in and out. Eventually, we're going to get to a Grafana screen, which will be make it a lot easier to see. I'm going to start the influx database, which is going to hold our metrics. This is all background stuff. Okay, this is the screen that matters. Is that large enough? Can we see what's happening?
Maybe you can make it a little bit larger. I just focused more on the screen here, but make it a little bit larger so that it's legible for everyone.
Does that work?
A little bit bigger, just a bit bigger, if we can.
How about that?
Yes, we can make out what it is.
Okay.
Everyone in the audience, are you okay with this view? Just put it in the chat. Give me a thumbs up.
Okay, I'm going to start up. Mongo database is needed for the application.
Yeah, you're good.
Okay. We're still not at the good part yet. I'm going to start up the JIT server. And lastly, I'm going to start up my Prometheus. Okay, so everything is running in the background that my application needs. So let's go ahead and start up my Acme Air containers. Again, there's 3 of them. They've all started. Now I'm going to run my JMeter, which is going to send traffic to all 3 of those containers. So let me show you what is in that. So you see my cursor? Hopefully yes. You can. Okay, so we have 3 Docker run commands. We're running the same application 3 times. The first one we're running with 400 megabytes. The second one with 200. Our third one also has 200, but it has these additional arguments at the end. The JIT server, which is this option here, which says use the JIT server located at this address on this port. Now, once that's running, now let's go out to see. This is the part that I'm hoping is still there. Where in? Oh, there it goes. So this is a Grafana chart. So at the top, can you see that?
Yes, we can.
Okay. So the top one here is running at 400 meg. First of all, the top row is not using the Samaroo cloud. So the top one is 400 meg, or the left one is 400 meg. The one on the right is 200 meg. And the one at the bottom here is also running at 200 meg, but with the Samaroo cloud. Now, if you notice, let's just take a look at these two that are running here on the left. The Samaroo cloud compiler version ramped up a lot faster, and it's getting to an optimized state. This is by the way, is CPU throughput. That's what we're measuring. So it's getting to an optimized state very quickly, and it's going to get to steady state here at this point. Now, the 400 meg without the Samaroo cloud compiler will also get there to a good steady state, but notice the ramp up time was a lot slower. And the important part here to look at is the version that's trying to run 200 meg. So this is an undersized container. You notice here that it's never going to get to an optimized state. The JVM is very smart, so it saw the requests for JIT compiles, but it just didn't have enough memory, so it's not going to do those. So it's basically running in interpreted mode. So that's the end of the demo. So what we've shown here is that we can, with the use of the Samaroo cloud compiler, we can run a container at half the size and be just as performant. So let me go back out to my let me start getting my little pencil thing going. I'm sorry, my laser pointer. You can see that. Okay. So again, just a little summary of the Samaroo cloud compiler. The JIT does provide advantages, but compilation adds overhead. So the solution is to disaggregate the JIT from the JVM, and we have a JIT compilation as a service. So the Samaroo cloud compiler is available now on these versions of Linux using IBM Samaroo runtimes. It's especially good for constrained environments like containers. It is Kubernetes ready, as you saw with the Liberty operator option, and it has Prometheus integration. It does improve ramp up, auto scaling, and performance of short-lived applications. So it's perfect for microservices. It can reduce the peak memory footprint and increase app density and reduce costs, which we showed in that one experiment. So there are some competing solutions, but they are proprietary, not open source, and do require additional licensing. So that's the one advantage of this approach here. So next we'll talk about Liberty InstantOn. So this solution, this technology is perfect for serverless functions or scaling to zero. So we talked earlier about that space on the right where we have a lot of new technologies coming in to handle the microservices serverless part of that chart, the right side of that chart, where Java traditionally struggled. So one of the main solutions to that problem is to do native image, which is a static compilation of your code. So basically like a C program, you compile it down to an executable and you run that. So there are some pros to that. It does provide a very small footprint. It's extremely fast, and it is good for short-lived applications. But there are some negatives. So one, you have a very limited JVM or no JVM. Static versus dynamic compiler optimization. Again, you'll never get to the level of optimization with a static compiler because you just don't know the environment that you're going to be running in. and it has limited garbage collection. So the longer it runs, the more potential for memory leaks, etc. Also, it has limited Java features. So a lot of the dynamic reflection, things like that, and access to all APIs. It is limited. And each of those has a moving target. They're all pretty new, again, with different frameworks, different ecosystem standards, and those are in a state of flux at this point because they're ever changing. They're brand new, right? So you'll have to go along for that ride as they make changes. The last con is that this concept of dev prod parity. This is one of the staples of cloud native development, is that you want to develop in an environment that's as close as possible to the production environment. So if you're running one of these tools that compiles into an executable, takes your Java code and compiles an executable, and you want it to run that as a test, as a developer, you're probably going to stick with a JVM for as long as you can, right? You don't want to go through that process of submitting changes, recompiles, restarts, rebuilds. You're probably going to be using that compiler. So that just adds another point that could be an issue as you get into your life cycles of development. So we have a solution. InstantOn has a solution called InstantOn, and we call it Java without compromise. So all the things that is talked about as cons don't exist with this solution. Basically, the thought is that we take a snapshot of an image, which we can then deploy. At that point, we can restore. So the concept comes from, or the basic foundation is Cryu, which is a Linux technology, which takes processes and does checkpoints, and then you can restore at the point where you checked. The same concept, but we've rolled it into application images. And as you can see on the chart on the right here, the startup times are significantly increased, sometimes seeing up to 15 times faster startup. So we're getting startup times in the milliseconds. And this chart here on the right is comparing Xamarin InstantOn with not using it and against Graal native image. So again, we get full Java support. You do not get full Java support with Graal native. High throughput, the longer the native image application runs, the less efficient it's going to be. And there's some concerns about how it does with load. So essentially, Graal native is geared toward short-lived applications. So satisfy requests and then close. So that's the base. That's their use case they're going for. InstantOn is a little more general, and it can happen. It can help all types of use cases. So again, the theory is during build time, what will happen is your container will reach a snapshot point. It'll run some hooks and then take that snapshot, and then it'll exit. So when you build your image, the end result will be an image that has been run and checkpointed and saved. So that image can then be taken to your runtime at a later point and just restored from that snapshot. Now, there are two places to snapshot, before app start and after app start. Obviously, the longer you take before you do the snapshot, the faster it's going to restart. But there are some limitations for why you would want to, or why you can't do it after app start. Mostly around connections, because obviously, if you really think about what's happening when you do a snapshot, there's a lot involved. Your code could be at multiple places with connections that have passwords, that have logins. All that stuff needs to be restored, If we can't, we need to roll the snapshot to before those things happen. Or roll the checkpoint to before those things happen. So again, there's these, we have 2 checkpoint phases: before app start, after app start. So here is a basic progression of an application. So the kernel start, how long it takes, we process the application, then we take an app start here. This is before app start. That's one of the options you can use. Here's the starting of the application, and then we have the additional start here, or the checkpoint done here. So the longer, if you do the checkpoint here, it's not going to come back as fast. If you do it here, it's going to come back as fast as it possibly can. Hopefully this will make more sense when we get into my demo. All right, back to our screen. How are we doing on time?
We are doing great on time. You have about 14 minutes.
Oh, perfect. Okay.
And we encourage anybody that has any questions to feel free to ask them in the chat or in the Ask a Questions tab.
Okay, now I have to find my window. Okay. I apologize, but I'm going to have to go out to another screen real quick. Lost. I apologize.
No worries at all.
I hope I can find this. Okay. I think I did. All right. All right, so we're going to show you an example of how InstantOn works. I've already built 2 images of an application. First of all, you can see the screen, correct?
Yes, we can see the screen.
Okay, I'm trying to make it as large as possible.
Everyone in the audience, or is the screen view okay for you? Thumbs up.
All right, so we have 2 Docker files to build this image. Nothing special here. Using a Java 11 OpenJ9 UBI, we're basically copying over the WAR file, and we're running this configure, which is an Open Liberty feature to optimize the code. Now, if I run that code, I'm going to start up this application locally, just to see how long it takes to load. So you can see here, I'm going to highlight this. It took 4.5 seconds to run. And this is what the application looks like here. Basically showing system properties for the host machine. So that took 4.5 seconds. I'll go ahead and kill that. Now I'm going to show you the Docker file for my InstantOn version. It's exactly the same. We have a UBI, the Java 11 OpenJ9 UBI. We copy in the WAR file. We run that configure script to optimize the code. But here we added one extra call. We're saying run the checkpoint after app startup. So when it created that image, it actually started the application, got to the application start point, did a checkpoint, and then saved that image and then killed it. So now it's ready to be run from that point. So if I run the InstantOn version, it took 400 milliseconds, a lot quicker, and it is still running. Okay, so that's running locally. Let's go ahead and run this in On the cloud, we're using Azure and Knative. I don't know if you guys are familiar with Knative, but it's an extension of Kubernetes, and it basically it gives you scale to zero capabilities. Now, if I did I'm looking at what's currently running, you'll see that there are no pods running. But I did push these images out to Knative, and you see that they're here. There's 2 versions running. And if I go to those URLs and I refresh those screens, it'll bring them back up. Now, if I do a get pods, you'll see that they're both running. I hope you could see this. This is kind of convoluted here. The screen's a little tight, but basically I have both of them are started because the pods were run. So Knative works that it goes idle, it goes away when it's not in use. But I just pinged both of those URLs, so it started up the pods and it's running them. Now, if I do this pods again, Knative looks, the timeout is about 30 seconds. So you notice they're both terminating because I haven't accessed those URLs again for the last 30 seconds. So these pods are going to go away. That's what scale to zero is, right? One is already gone. Let's wait till they're both totally gone, and then let's see how long it takes for Knative to bring those back. Okay, they're both gone. So we'll do a little experiment. I'm going to count out loud. This will just be a visual test. So here's the first version that does not have an InstantOn image. So let's go ahead and start this. I'm going to click this button and see how long it takes to refresh. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that took about 11 seconds. And we'll prove that by looking at the pods. You'll see 1 pod. There it is. Now we'll try the version that has an InstantOn image. Again, I'll count. 1, 2. So it's already back. And most of that time is spent with Knative actually cold starting back up. Typically that is around a 2 to 4 second delay that happens with just Knative. So before it even gets to the point of trying to load the image, it takes 2 to 3 seconds. So that was basically instantaneous. So that is that demo. By the way, I'm very happy that I was able to do both of those. Okay, play from current slide. So we're back to our screens. We're almost done here. So here's a good, I will have these slides available later. So here's a lot of good links to blogs, and interesting talks about how InstantOn works, a lot of the technology behind it. So let's go ahead and wrap this up. Again, remember that initial screen I had where we talked about the architecture styles and how they fit with traditional runtimes. We had a lot of red marks over here on the, oh, my laser pen went away. Sorry, let me just get that real quick. So over here we had a lot of red marks, but with Liberty, so monoliths obviously are going to work with Liberty and Xamarin runtimes. Same with microservices. Microservices now we can check that green because we have Xamarin runtimes with the Xamarin Cloud compiler. And serverless functions, we now have a green mark because we have access to Xamarin runtimes with InstantOn. So here's a good website. This is the Open Liberty IO website. Here I'm pointing to the guides section, which is really good. So if you want to learn about Open Liberty, this is a great way to do it. There's a lot of technologies here on the left that you can learn about through the use of code. Each one of these is about 20 to 30 minutes. The really cool part about this is you can run these in the cloud. So if you start it up, you'll run it in the cloud. It brings up an IDE, I think it's VS Code, gives you code snippets. You can just drag and drop. You can add to the application and run it, and you get to learn about different technologies such as persistence or microservices or RESTful APIs, etc. A really great site to learn on. And again, you can run on the cloud, so you don't have to download anything to your local computer. Here's some more useful links about learning about Open Liberty. I do want to mention that a couple of my colleagues are going to be presenting here on October 31st, 10 a.m. Eastern Time, around InstantOn. So they're going to take a real deep dive into InstantOn. I covered it in 5 minutes. They're going to spend a whole hour on it. Definitely tune into that. And that's it for me. I appreciate you reaching out. If you have any questions, that pointer at the bottom is. And yes, I'm always available. Love to hear from you if you have any questions. That's it for me. Thank you very much.
Thank you so much for the excellent presentation today, Rich. And a reminder, and anyone in the audience, if you do have any final questions, please put them in the chat. I also like to add a little reminder that we are looking now officially to book some Jakarta Tech Talks in 2024. So if you're interested in presenting, feel free to fill out the form that I linked in the chat. And finally, if you have feedback on the Tech Talk program, we would love to hear from you. So just click on the green button that will pop up at the end of this webinar and let us know. We hope you enjoyed the talk today, and I'll just take a quick look in the Ask a Questions. We do have one question. So we have a question from Mario Leonard Reamer, and he is asking, are you aware of any other projects and runtimes to make use of OpenJ9 and CRIU checkpoints restore functionality?
So Samaru is the only one, or Open Liberty is the only runtime that uses OpenJ9. There are other technologies out there that are trying to leverage the CRIU Linux technology, Crack for one. I think that's it. So I think that was his question, right?
Perfect.
Yeah, Azul Crack uses CRIU.
Perfect. Mario, was that did that answer your question? Can you give a thumbs up? Anyone else in the audience have any other questions for Rich today? All right.
Great.
That is it. Thank you so much again, and have yourselves all a beautiful rest of your day or evening wherever you are in this beautiful world.
Thank you. Thank you. Bye-bye.